Chapter 17 was called Toxic Cleanup, and it mainly focused on solid toxins as a way to introduce us into precipitation reactions and stoichiometry. A precipitate is a solid that forms as the result of two solutions mixing together. In this reaction here, you have a solution of potassium chromate and barium nitrate mixing together. It's a double replacement reaction, which means the two positive cations are going to swap places, and instead of potassium chromate, you're going to have potassium nitrate that forms and barium chromate. This reaction here, this is just showing you what is in the two solutions. So potassium chromate, because it's aqueous, it dissolves in water, it splits up into potassium and chromate ions, and the barium nitrate also splits up into barium and nitrate ions. But when this reaction happens, the aqueous potassium chromate mixes with the aqueous barium nitrate, and you get aqueous potassium nitrate, and you get solid barium chromate. That is your precipitate that forms. It's the solid that forms from the two solutions. Now I know that the potassium nitrate is going to be aqueous because we checked the solubility guidelines or the solubility rules. Nitrates, compounds that contain them, are always soluble. There's no exceptions. And then barium chromate, it's not on our solubility guidelines, so you wouldn't be able to be asked about a chromate containing compound, but most chromates they're like carbonates and phosphates. Most of them are insoluble unless they contain a group 1 ion. I gave you 3 examples below, to try writing out the double replacement reactions. So potassium nitrate and barium chloride, sodium sulfate and lead 2 nitrate, and then potassium hydroxide and barium nitrate. If you want to take a minute to try these, stop the video, write out what the products would be, correct chemical formula, use the solubility guidelines to check the name or the solubility for each of them to determine if it's going to be soluble or insoluble, if it's going to be aqueous or a solid. You should get aqueous potassium chloride and aqueous barium nitrate here. So we would observe no reaction for this one because you're just mixing two solutions to get two solutions, no solid forms. You're going to get sodium nitrate, aqueous, and lead 2 sulfate, which is insoluble. It's a solid. Sulfates are soluble except if it contains strontium, barium, mercury, or lead, which that fits. Here you're going to get potassium nitrate, which is soluble. And you're going to get barium hydroxide, which here hydroxides are insoluble except when they contain alkali metals, calcium, strontium, or barium. So this is actually aqueous as well. So again, for this one, there's no reaction observed. So this one gives us a reaction and the precipitate is there. I'm not balancing the equations here, but if the question asked for you to balance the equation, you would go ahead and balance the equation to conserve mass. We used the precipitation reactions to look at mole ratio. We did a lab where we combined the reactants in different ratios to see that we would get the most product when we combined the reactants in the mole ratio. The mole ratio is looking at the coefficients from the balanced chemical equation. It's the ratio in which the reactants react and the products form. So here for this reaction, for the production of ammonia, it's 1 mole of N2 to 3 moles of H2 to form 2 moles of NH3. Every time that reaction occurs, it occurs in that specific ratio. So for example, if we're starting here with 3 moles of N2 and 1, 2, 3, 4, 5, 6 moles of H2, how far can the reaction go? Well, 1 of these will combine with 3 of these to give us 2 of those. The reaction can continue again. 1 of those will react with 3 of these to produce 2 of those. So as far as I can go, the reaction will produce a max of 4 moles of ammonia with H2 being the limiting reactant that limited how far I can go, and 1 mole of N2 left over in excess. Last thing we looked at was stoichiometry, which was really just mathematical calculations for how much of a reactant you would need or how much product is formed. Of course, we need the balanced equation from the mole, or the mole reaction from the balanced equation in order to do the stoichiometry calculations. How many moles of nitrogen are needed to produce 18 moles of ammonia? Remember, this up here is the mole ratio. So the only thing we can use these numbers for is going to and from mole amounts of reactant and product, which this question is doing. So we're starting with 18 moles of ammonia. I want to go to figure out how many moles of nitrogen. Well, I can figure that out from the equation because the mole ratio between ammonia and nitrogen is 2 to 1. 2 moles of NH3 form for every 1 mole of N2 that reacts. 18 divided by 2 gets you 9. It's 9 moles of N2. How many grams, that should throw up the red flag, of ammonia will be produced if 9 moles of hydrogen react? We're starting with 9 moles of H2, but there's nothing in this mole ratio that can get me from moles to grams right away. So the only thing we can do first is go from moles of hydrogen to moles of ammonia. What's the mole ratio? 3 moles of hydrogen react for every 2 moles of ammonia that form. And then we want to go to grams of ammonia. That's from another chapter. We can go from moles to grams or grams to moles by using the molar mass. Calculate the molar mass of ammonia. 17. Make sure your units cancel. So we're going to do 9 times 2 times 17 divided by 3. And we should get 102 grams of ammonia. How many grams of hydrogen are needed to react with 10 grams of nitrogen? Again, the grams should throw up the red flag. I can't do anything with that grams right away in the mole ratio until I convert it to moles. So I'll use the molar mass of nitrogen, which is 28, for every 1 mole of N2. Now that I have moles of N2, I can use the mole ratio from the equation to go from moles of N2 to moles of H2 using the mole ratio, which is 1 mole of N2 reacts for every 3 moles of H2 that react. And they don't want me to stop at moles of H2, they want me to convert to grams of H2 using the molar mass. So 1 mole of H2 has a mass of 2 grams. The math is 10 times 3 times 2 divided by 28, and I get 2.14 grams of H2. What is the maximum number of moles of ammonia that can form when 5 moles of nitrogen react with 13 moles of hydrogen? So you can do this mathematically, or you can do it by just drawing out a picture. So we'll do 13 moles here. 9, 2, 4, 6, 13. We have to use the mole ratio in which they react in. So for every 1 mole of N2, 3 moles of H2 are going to react to give you 2 moles of ammonia, as per the balanced equation. 1, 3, 2, 1, 3, 2, 1, 3, 2. And then that's the furthest this reaction can go. This question's a little bit different than the ones that we were used to looking at in class. So I would not worry about being asked a question like this where the numbers don't work out. This question is a little bit different than the ones numbers that work out where all of it's we were used to looking at in class. All of one reactant so consumed, and then one would not worry about over, but if we just look at what we have left, a question like this with this mole of N2 and the mole of H2, where the numbers don't work out first, and if we think about it like for a minute, in the final exam, the numbers would work out where all of it's one mole of N2, you need all of one reactant's equation, 3 moles of H2 but left over. But if we just look at what we have left with this mole of N2 and the mole of H2, one is going to be used first, and if we think about it for a minute, H2. If you have 1 mole of N2, you need, according to the balance equation, 3 moles of H2. This will be used up first, which you don't have. So H2 is your limiting, because you're going to have less than 1 mole of N2 left, because some of that is going to be used. It's not going to be a whole number in terms of moles. So that's why we shouldn't worry about this will be used up first. A problem like this, your numbers would work out. So if you were asked H2 is your limiting, you're going to have less than 1 mole of N2 left, because some of that is going to be used. It's not going to be a whole number in terms of moles. So that's why we shouldn't worry about a problem like this. Your numbers would work out if you were asked a question like this.